In this video, I will show you how you can persist data in Kubernetes using volumes. We will cover three components of Kubernetes storage: persistent volume claim, and storage class, and see what each component does and how it's created and used for data persistence. Consider a case where you have a MySQL database pod which your application uses. Data gets added, updated in the database. Maybe you create a new database with a new user, etc. By default, when you restart the pod, all those changes will be gone because Kubernetes doesn't give you data persistence out of the box. That's something that you have to explicitly configure for each application that needs saving data between pod restarts. So basically you need a storage that doesn't depend on the pod lifecycle, so it will still be there when pod dies and new one gets created. So the new pod can pick up where the previous one left off. So it will read the existing data from that storage to get up-to-date data. However, you don't know on which node the new pod restarts, so your storage must also be available on all nodes, not just one specific one, so that when the new pod tries to read the existing data, the up-to-date data is there on any node in the cluster. And also you need a highly available storage that will survive even if the whole cluster crashed. So these are the criteria or the requirements that your storage, for example, your database storage, will need to have to be reliable. Another use case for persistent storage, which is not for database, is a directory. Maybe you have an application that writes and reads files from pre-configured directory. This could be session files for application or configuration files, etc. And you can configure any of this type of storage using Kubernetes component called persistent volume. Think of a persistent volume as a cluster resource, just like RAM or CPU, that is used to store data. Persistent volume, just like any other component, gets created using Kubernetes YAML file, where you can specify the kind, which is persistent volume, and in the specification section, you have to define different parameters, like how much storage should be created for the volume. But since persistent volume is just an abstract component, it must take the storage from the actual physical storage, right? Like local hard drive from the cluster nodes, or your external NFS servers outside of the cluster, or maybe cloud storage like AWS, block storage, or from Google Cloud Storage, etc. So the question is, where does this storage backend come from? Local or remote or on cloud? Who configures it? Who makes it available to the cluster? And that's the tricky part of data persistence in Kubernetes, because Kubernetes doesn't care about your actual storage. It gives you persistent volume component as an interface to the actual storage that you as a maintainer or administrator have to take care of. So you have to decide what type of storage your cluster services or applications would need and create and manage them by yourself. Managing meaning do backups and make sure they don't get corrupt, etc. So think of storage in Kubernetes as an external plugin to your cluster. Whether it's a local storage on actual nodes where the cluster is running or a remote storage, doesn't matter, they're all plugins to the cluster. And you can have multiple storages configured for your cluster, where one application in your cluster uses the local disk storage, another one uses the NFS server, and another one uses some cloud storage. Or one application may also use multiple of those storage types. And by creating persistent volumes, you can use these actual physical storages. So in the persistent volume specification section, you can define which storage backend you want to use to create that storage abstraction or storage resource for your applications. So this is an example where we use NFS storage backend. So basically we define how much storage we need, some additional parameters to that storage, like should it be read-write or read-only, etc. and the storage backend with its parameters. And this is another example where we use Google Cloud as a storage backend, again with the storage backend specified here and capacity and access modes here. Now, obviously, depending on the storage type, on the storage backend, some of the attributes in the specification will be different because they're specific to the storage type. This is another example of a local storage, which is on the node itself, which has additional node affinity attribute. In the official Kubernetes documentation, you can actually see the complete list of more than 25 storage backends that Kubernetes supports. Note here that persistent volumes are not namespaced, meaning they're accessible to the whole cluster, and unlike other components that we saw like pods and services, they're not in any namespace. They're just available to the whole cluster, to all the namespaces. Now, it's important to differentiate here between two categories of the volumes, local and remote. Each volume type in these two categories has its own use case. Otherwise, they won't exist. And we will see some of these use cases later in this video. However, the local volume types violate the second and third requirements of data persistence for databases that I mentioned at the beginning, which is one, not being tied to one specific node, but rather to each node equally, because you don't know where the new pod will start. And the second, surviving in cluster crash scenarios. Because of these reasons, for database persistence, you should almost always use remote storage. So who creates these persistent volumes and when? As I said, persistent volumes are resources like CPU or RAM. So they have to be already there in the cluster when the pod that depends on it or that uses it is created. So a side note here is that there are two main roles in Kubernetes. There's an administrator who sets up the cluster and maintains it, and also makes sure the cluster has enough resources. These are usually system administrators or DevOps engineers in a company. And the second role is Kubernetes user that deploys the applications in the cluster either directly or through CI pipeline. These are developer DevOps teams who create the applications and deploy them. So in this case, the Kubernetes administrator would be the one to configure the actual storage, meaning to make sure that the NFS server storage is there and configured, or maybe create and configure a cloud storage that will be available for the cluster. And second, create persistent volume components from these storage backends, based on the information from developer team of what types of storage their applications would need. And the developers then will know that storage is there and can be used by their applications. But for that, developers have to explicitly configure the application YAML file to use those persistent volume components. In other words, application has to claim that volume storage. And you do that using another component of Kubernetes called persistent volume claim. Persistent volume claims, also PVCs, are also created with YAML configuration. Here's an example claim. Again, don't worry about understanding each and every attribute that is defined here. But on the higher level, the way it works is that PVC claims a volume with certain storage size or capacity, which is defined in the persistent volume claim, and some additional characteristics like access type. Should it be read-only or read-write, or the type, etc. And whatever persistent volume matches this criteria, or in other words, satisfies this claim, will be used for the application. But that's not all. You have to now use that claim in your pod's configuration, like this. So in the pod specification here, you have the volumes attribute that references the persistent volume claim with its name. So now the pod and all the containers inside the pod will have access to that persistent volume storage. So to go through those levels of abstraction step by step. Pods access storage by using the claim as a volume, right? So they request the volume through claim. The claim then will go and try to find a volume, persistent volume in the cluster that satisfies the claim. And the volume will have a storage, the actual storage backend that it will create that storage resource from. And this way, the pod will now be able to use that actual storage backend. Note here that claims must exist in the same namespace as the pod using the claim, while, as I mentioned before, persistent volumes are not namespaced. So once the pod finds the matching persistent volume through the volume claim, through the persistent volume claim, the volume is then mounted into the pod like this here. This is a pod level. And then that volume can be mounted into the container inside the pod, which is this level right here. And if you have multiple containers here in the pod, you can decide to mount this volume in all the containers or just some of those. So now the container and the application inside the container can read and write to that storage. And when the pod dies, a new one gets created. It will have access to the same storage and see all the changes the previous pod or the previous containers made. Again, the attributes here like volumes and volume mounts, etc., and how they're used, I will show you more specifically and explain in a later demo video. Now, you may be wondering why so many abstractions for using volume, where admin role has to create persistent volume and user role creates a claim on that persistent volume, and that is then used in pod. Can I just use one component and configure everything there? Well, this actually has a benefit because as a user, meaning a developer who just wants to deploy their application in the cluster, you don't care about where the actual storage is. You know, you want your database to have persistence, and whether the data will live on a Gluster FS or AWS EBS or local storage doesn't matter for you, as long as the data is safely stored. Or if you need a directory storage for files, you don't care where the directory actually lives, as long as it has enough space and works properly. And you sure don't want to care about setting up this actual storage yourself. You just want 50 gigabyte storage for your Elastic or 10 gigabyte for your application. That's it. So you make a claim for storage using PVC and assume that cluster has storage resources already there. And this makes deploying the applications easier for developers because they don't have to take care of the stuff beyond deploying the applications. Now, there are two volume types that I think needs to be mentioned separately because they're a bit different from the rest, and these are config map and secret. Now, if you have watched my other video on Kubernetes components, then you are already familiar with both. Both of them are local volumes, but unlike the rest, these two aren't created via PV and PVC, but are rather own components and managed by Kubernetes itself. Consider a case where you need a configuration file for your Prometheus pod, or maybe a message broker service like Mosquito, or consider when you need a certificate file mounted inside your application. In both cases, you need a file available to your pod. So how this works is that you create config map or secret component, and you can mount that into your pod and into your container the same way as you would mount persistent volume claim. So instead you would have a config map or secret here. And I will show you a demo of this in a video where I cover local volume types. So to quickly summarize what we've covered so far, as you see at its core, a volume is just a directory, possibly with some data in it, which is accessible to the containers in a pod. How that directory is made available or what storage medium actually backs that, and the contents of that directory are defined by a specific volume type you use. So to use a volume, a pod specifies what volumes to provide for the pod in the specification volumes attribute, and inside the pod then you can decide where to mount that storage into using volume mounts attribute inside the container section. And this is a path inside the container where application can access whatever storage we mounted into the container. And as I said, if you have multiple containers, you can decide which containers should get access to that storage. Interesting note for you is that a pod can actually use multiple volumes of different types simultaneously. Let's say you have an Elasticsearch application or pod running in your cluster that needs a configuration file mounted through config map, needs a certificate, let's say a client certificate mounted as a secret, and it needs database storage, let's say, which is backed with AWS Elastic Block Storage. So in this case, you can configure all three inside your pod or deployment. So this is the pod specification that we saw before. And here on the volumes level, you will just list all the volumes that you want to mount into your pod. So let's say you have a persistent volume claim that in the background claims persistent volume from AWS block storage. And here you have the config map, and here you have a secret. And here in the volume mounts, you can list all those storage mounts using the names, right? So you have the persistent storage, then you have the config map and the secret, and each one of them is mounted to a certain path inside the container. Now we saw that to persist data in Kubernetes, admins need to configure storage for the cluster, create persistent volumes, and developers then can claim them using PVCs. But consider a cluster with hundreds of applications where things get deployed daily and storage is needed for these applications. So developers need to ask admins to create persistent volumes they need for applications before deploying them. And admins then may have to manually request storage from cloud or storage provider and create hundreds of persistent volumes for all the applications that need storage manually. And that can be tedious, time-consuming, and can get messy very quickly. So to make this process more efficient, there is a third component of Kubernetes persistence called storage class. Storage class basically creates or provisions persistent volumes dynamically whenever PVC claims it. And this way, creating or provisioning volumes in a cluster may be automated. Storage class also gets created using YAML configuration file. So this is an example file where we have the kind storage class. Storage class creates persistent volumes dynamically in the background. So remember, we defined storage backend in the persistent volume component. Now we have to define it in the storage class component. And we do that using the provisioner attribute, which is the main part of the storage class configuration because it tells Kubernetes which provisioner to be used for a specific storage platform or cloud provider to create the persistent volume component out of it. So each storage backend has its own provisioner that Kubernetes offers internally, which are prefixed with kubernetes.io, like this one here. And these are internal provisioners. And for others or other storage types, they are external provisioners that you have to then explicitly go and find and use that in your storage class. And in addition to provisioner attribute, we configure parameters of the storage we want to request for our persistent volume, like these ones here. So storage class is basically another abstraction level that abstracts the underlying storage provider as well as parameters for that storage, or characteristics for the storage, like what disk type or etc. So how does it work, or how do we use storage class in the pod configuration? Same as persistent volume, it is requested or claimed by PVC. So in the PVC configuration here, we add additional attribute that is called storage class name that references the storage class to be used to create a persistent volume that satisfies the claims of this PVC. So now when a pod claims storage through PVC, the PVC will request that storage from storage class, which then will provision or create persistent volume that meets the needs of that claim using provisioner from the actual storage backend. Now, this should help you understand the concepts of how data is persisted in Kubernetes as a high-level overview.